So, welcome you all, welcome in my next lecture. So, in my last lecture I talked about change of variable formula. My plan is to talk about if I have a cylindrical coordinate system or say spherical coordinate system, then how the change of variable formula or using change of variable formula, how I can replace my double integral or triple integral in that Cartesian coordinate system to the corresponding cylindrical coordinate system or spherical coordinate system, and using that I can maybe it might be easy to calculate those triple integral. So, that is couple of examples I will talk about that, and what about the corresponding transformation in the setting of cylindrical coordinate system and spherical coordinate system, how it is going on. So, that is the kind of part in this lecture I am planning to talk about. Okay. So, as I said, so in my last class I talked about this what is called change of variable for multiple integrals. Well, for n is equal to 3, this is nothing but the triple integral. So, what is that? I already discussed. Again I am just what is called recall that what is change of variable formula. So, it says that if I have a open bounded set in Rn and if I have a transformation T which is C1, C1 means it is continuously differentiable, that means partial derivative, first order partial derivative exists and they are continuous. If it is injective, at the same time Jacobian of this transformation T at the point u is non-singular, that means the determinant is non-zero. If that is the case, and if I say that G is nothing but the image of the domain D under the transformation T, and if it is given that my function f from G to R is integrable, then I can change the variable x1, x2, xn to u1, u2, un. Okay. And how it works? So, this is the formula dx1, dx2, dxn. It is nothing but du1 up to dun, provided you have to hit it by a factor. And what is that factor? The factor is that what is the del x1, x2, xn divided by del u1, u2, un. In other words, actually you can have the function x1 which is nothing but x1 of u1, u2, un, okay, and up to xn which is xn of u1, u2, un. So, these functions are nice, that means partial derivative exists and continuous. Then this is nothing but the Jacobian of this transformation T at the point u. In other words, this is nothing but the first you have to consider the Jacobian matrix, that means this is nothing but del x1. So, it is n cross n matrix, right. So, in fact, the determinant of the n cross n matrix Jacobian, not the Jacobian matrix. So, Jacobian matrix, if I take the determinant, it is called the Jacobian, and then you have to take the what is called absolute value. So, what is that? So, this is nothing but x1, x2, xn. So, that means what you have to do? So, that means del x1 del u1 del x2 del e1, so and up to del xn del e1. Okay. So, first in the row you take x1, x2, xn, take the partial derivative with respect to u1 variable. Next is that same thing with respect to u2 variable, and finally you have del x1 up to del un variable, and that will give you n cross n matrix. This is called the Jacobian matrix, I should say. This is a matrix, n cross n matrix. If I take the determinant, this is called the Jacobian, and you have to take the absolute of that. So, this how the what is called change of variables things happening, and therefore, the corresponding multiple integral, that means if I integrate over the domain G in my x1, x2, xn variable of my functions f of x, where x actually x1, x2, xn, which is a functions of u1, u2, un, as I said. So, if I integrate my function in the variable x1, x2, xn over the domain G, so this exactly equal to, if I change it to another variable, that means u1, u2, un, then the corresponding domain will change, because G is nothing but Td, because now I am in the domain D and the corresponding variables are u1, u2, un. So, therefore, du1, du2, dun, and then the corresponding integral will change, because x will change by x of u, because I am in the domain u1, u2, un. Okay. And in the domain D where variables are u1, u2, un, then you have to hit it by this extra factor, which is nothing but the Jacobian of x1, x2, xn with respect to u1, u2, un, and you have to take the absolute value. And in short form I am writing f of xu absolute of dx du times du. This is a notation. Okay. So, du stands for du1 up to dun, and this absolute of dx by du, this is nothing but the del x1, x2, xn divided by del u1, u2, un, which is nothing but a determinant of the n cross n matrix whose elements are like this one. Okay. So, that is how the change of variable formula will work. Now, in the special case, like I know in the 3-dimensional Euclidean space, I have a what is called Cartesian coordinate system along with that I have what is called cylindrical coordinate system and spherical coordinate system. Then let us see if I change this Cartesian coordinate system to the spherical or cylindrical coordinate system, how the change of variable formula or what sort of integral will transform. So, that we will see. So, that is what I have written, triple integrals in cylindrical coordinates. So, cylindrical coordinates I have written. So, a cylindrical coordinate system consists of polar coordinates r theta in a plane together with a third coordinates z, which measures along in the axis perpendicular to the r theta plane, which is nothing but the xy plane. So, therefore, what we have? So, this is my what is called x and this is my y and this is my z. So, now in the xy plane, so this is actually what we will solve. This is the plane xy plane, this is nothing but r theta plane I will have, okay, r theta, and the z as it is, that means it is perpendicular to the like xy plane, similarly it is perpendicular to the r theta plane, okay, that is exactly I have written. This means that the z coordinate is the cylindrical coordinate system is the same as z coordinate in the Cartesian coordinate system. So, what I am doing? So, I have a xyz plane, now this time what I am doing, xy plane I am transformed to a r theta plane, okay, and z plane as it is, which is perpendicular to the xy plane. So, now the corresponding, so I have a xyz plane, right, the Cartesian coordinate system. So, now I am transforming to the r theta z plane. What is the transformation? In the xy plane I am thinking this as a r theta plane and z is nothing but the perpendicular to the r theta plane. So, therefore, my coordinate system xyz transform to r comma theta comma z, and that is called the cylindrical coordinates. Okay. So, I just draw a picture. So, triple integrals in cylindrical coordinates, as I said, this is my xy plane, right, this is my xy plane. Now, I am just changing to a r theta plane. What is r? So, if I take any point, r is nothing but the distance from the origin of that point and theta is nothing but the angle of the point. So, if I have a point P, say let it be P, then draw a line from the origin, okay, and then you have to measure the angle in the anticlockwise directions from the x axis, that I am denoting as theta. So, therefore, each point in the xy plane I can represent it as a point like r comma theta. What is r? R is nothing but the distance of my point in the xy plane from the origin. And what is my theta? Theta I can have the angle in the anticlockwise directions from the positive x axis if I take. So, that is called the theta, and I draw a picture. So, this is the positive x axis. So, this is my point, this is my distance from the origin, and now I am measuring my theta in the anticlockwise directions of that point. Okay. So, this is called r theta, and z as it is, z is nothing but the perpendicular to the xy plane earlier in the Cartesian coordinate system, and in time also r theta plane it is perpendicular. So, this is any point I can have the representation like r theta and comma z. But of course, there is a formula, like if I have a two-dimensional plane and if I have a polar coordinate, there is a relation, x is equal to r cosine theta, y is equal to r sine theta, and z as it is. So, if I write x, y, z, like x is equal to r cosine theta, y is equal to r sine theta, and z is equal to z, then the corresponding system is called the what is called cylindrical coordinate system. Okay, let us see. Yes. So, triple integrals in cylindrical coordinate system. So, this is the remark. The relations between cylindrical coordinate and rectangular coordinate is given by x is equal to r cosine theta, y is equal to r sine theta, and z, this is as it is. What is my r? R is the point, in fact the point xyz in the r3 plane, which is the projections into the what is called xy plane or r theta plane, and then take the distance of that point from the origin, and which is nothing but x square plus y square. And what is your theta? Theta is nothing but tan inverse of y by x, because look at the picture, this is my theta. So, this is x, this is y. So, this is like by trigonometric formula, theta is tan inverse y by x, and r is nothing but the distance from the origin to the point this one, which is nothing but x comma y. So, this distance is nothing but r square is equal to x square plus y square, right. So, polar coordinate system in the two-dimensional plane, you know the same thing, you just take the polar coordinate system in the two-dimensional plane and keep z as it is, and that will give you what is called cylindrical coordinate system. So, that is what the relations, x is equal to r cosine theta, y is equal to r sine theta, and z as it is. Okay. Once I have this one, now let us see that how the triple integral in the cylindrical coordinate system. Suppose you have given a triple integral in the Cartesian coordinate system. So, now I want to change this triple integral from the Cartesian coordinate system to the cylindrical coordinate system. That means I am changing the variable. That means there is a change of variable I am doing. So, in the Cartesian coordinate system I have the variable x, y, z, but in the cylindrical coordinate system I will have the variable what is called r, theta and z, and there is a relation between x, y, z with r and theta. R theta z. So, now if I have this, So if I want to change x, y, z to r theta z, like I know what is the change of variable formula says. So if I apply that one, then what is there is that let D be a simple region in R3, very nice region. Then the corresponding triple integral, that means that this is the triple integral in the Cartesian coordinate system, where my integrand is f of x, y, z, and this is dx, dy, dz. This time I can also write like dv. Okay. So now this triple integral will change it to a new variable like in the cylindrical coordinate system. Of course, the corresponding function x, y, z replaced by f of r theta z. Of course, the integrand will change depending on the functions, what functions I am taking in the x, y, z variable, and now I have to change it to a r theta z variable, and there is a relations between x, y, z with r theta z, like x is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. Then the corresponding integrand will be there, the change integrand will be there. Along with you have dr, d theta, dz, that is the variable, that as it is. Now the extra factor will come from the fact like the Jacobian determinant of this Jacobian, like del x1 x2 xn divided by del u1 u2 un absolute, that is the extra factor, and that extra factor will contribute what is called, this is your r, this is r. Okay, I just put a line on the r, so this is actually r. I will compute in my next slides. You will see exactly r will come. Just means what? You have to just calculate the Jacobian matrix. You have to take the determinant, that means from the Jacobian, and take the absolute, and that will exactly give you the r. Because I have a relation x in terms of r theta z, y in terms of r theta z, and z in terms of r theta z. And you have to just perform the partial derivatives, get a Jacobian matrix, take the determinant, get the Jacobian, and take the absolute. Okay. And of course, you have to be very careful, the corresponding domain will change, right. So now in the Cartesian coordinate system, you have the domain D. Now you have to have a transformation, that means the corresponding change of variable will be there, and using that transformation, of course, the integrand will change. At the same time, the domain where you have to integrate in the new what is called coordinate system, that is nothing but the cylindrical coordinate system. In that domain, the corresponding domain will change, and that I am denoting as d star. So where d star is the region corresponding to d in the r theta z space. So this is the new coordinate system, right, r theta z space. So you have a d in the x, y, z space, right, in the Cartesian coordinate system. Now the corresponding domain, using the transformation, the domain of integration will change to some domain in the r theta z space, okay, using the transformation. Okay. So if I calculate one example, then it will be more clear. Look, so before that I just convince you, yes, look, that this integral is nothing but the corresponding integral in the what is called cylindrical coordinate system, where you have the corresponding changes of the integrand, the domain, and this is should be there dr d theta dz, because in this variable I am talking about, but there will be an extra factor, and how the extra factor is coming, this is coming actually from the transformation, and in fact you have to consider the Jacobian matrix, then take the determinant and take the absolute. So why? Because look, so this is the transformation I am using, t of r theta z, which is r cosine theta, r sine theta, and z. In other words, this I can write it as t of r theta z, this is nothing but x of r theta z, comma y of r theta z, comma z of r theta z. So this is the one, and what is my x of r theta z? X of r theta z, which is nothing but r cosine theta. Y is a function of r theta z, which is nothing but r sine theta, and z is a function of r theta z, which is nothing but z itself, right. So now I have, see, x, y, z, I have the Cartesian coordinate system, and corresponding I have a functions x as r theta z, y as r theta z, and z of r theta z. Using this transformation, t of r theta z, which is nothing but x is nothing but as a functions of r theta z is r cosine theta, y I can think about as a function of r theta z, which is nothing but r sine theta, and z is a function of r theta z, which is nothing but the function z itself. Now you have to calculate the Jacobian, that means you have to perform, what is this? This is del of x, y, z divided by del r theta comma z, which is nothing but, you have to first calculate the Jacobian matrix, which is nothing but what? Which is nothing but del x del r, and then what? Del x del theta. So del x del theta and del x del z, that is one. Then del y del r, del y del theta, and del y del z, and finally you have del z del r, del z del theta, del z del z. So this is the corresponding Jacobian matrix. So that means first row you take the function x perform the partial derivative with respect to variable r, theta and z. In the second row, so this is the first row. In the second row, think about the functions y as a function of r, theta, z, which is given here, and you have to perform the derivative, partial derivative with respect to r, theta, z. And at the end, in the third row, you consider the function z, which is a function of r, theta, z, which is given here, and you have to perform the derivative with respect to partial derivative with respect to the variable r, theta and z. You just perform it. So what is del x del r? X of r, theta, z is given r cosine theta. So del x del r is nothing but what? Cosine of theta, because theta is just because I am taking the partial derivative with respect to r. So that means I have to think about theta is constant, that means cosine theta is constant. If I take the derivative with respect to r, so this will be 1, so that means you will have cosine theta. What will happen? Del x del theta. Now it is del x del theta means now this time I am considering r is constant and you have to perform the derivative with respect to theta. Now what is the derivative of cosine theta? That means minus of r sine theta. And what about del x del z? Now there is no part of z in x, so therefore del x del z or partial derivative of x with respect to z variable is 0. Similarly, do del y del r, del y del theta and del y del z, that means partial derivative of y with respect to the variable r, theta and z. Again del y del r, if I do that, again keeping the theta is constant, this is nothing but sine theta, and then finally then next one del y del theta means keeping r is constant, that means it is r cosine theta. Again this will be 0 because there is no variable z there in the function y. So therefore del y del z is 0. And what about the last row? So del z del r, again z, the function z which is a function of r, theta, z is independent of r and theta. So therefore del z del r and del z del theta, both of them are 0, and the last one del z del z, which is exactly give you the 1, because I am taking the partial derivative of z with respect to partial derivative of z with respect to the variable z. So therefore this will give you 1. So this is the Jacobian matrix. You take the determinant. This is the determinant, you calculate it just using the simple formula of determinant, you will end up with this is r. Now r is positive, so whether I am taking the absolute or keep, so no matter. So therefore the corresponding dv, that means dv means what? Dx dy dz. So that means dx dy dz, which actually changes to dr d theta dz, and this extra factor is coming from here. So therefore the corresponding triple integral or Riemann-Darboux integral with respect to the Cartesian coordinate system, and this is dv, changes to, of course that you have to be careful, the corresponding domain will change because I am in the different coordinate system, that is r, theta, z, that means the domain will change, and at the same time this is d star, and at the same time of course the integral will change, because if I have a coordinate system x, y, z, then if I transform to the new coordinate system r, theta, z, then the corresponding integrand will change. You will have dr d theta dz, that as it is, and the extra factor r is coming because of this Jacobian business. Okay. So this is the corresponding change of variable from the Cartesian coordinate system to the cylindrical coordinate system. Let us calculate one example explicitly. So this is the one. For example, evaluate this triple integral which is given in the Cartesian coordinate system. This is actually, this is a notation, right? This you can write it as dx dy dz, okay, dv, where g is the region bounded by x square plus y square is equal to 1, z is equal to 4, and z is equal to 1 minus x square minus y square. So now therefore that coordinate system, so Cartesian coordinate system is given. Now I want to change it to the corresponding what is called cylindrical coordinate system. So first of all, that domain or the region that I want to integrate or I want to integrate my function square root of x square plus y square over the domain G, and if I wanted to shift or change of variables from the Cartesian to the cylindrical one, then first I have to see what will be the corresponding region in the cylindrical coordinate system, and that exactly I have written. So consider the cylindrical coordinate system, then the corresponding domain in the cylindrical coordinate system reduced to r theta z, where r theta running from closed interval 0 to 1, theta running from 0 to 2 pi, and you see, look, z is equal to 4 and z is equal to 1 minus x square minus y square. And what is x square plus y square? X is equal to r cosine theta, y is equal to r sine theta. That means it will tell you that if I put x square 1, this is nothing but 1 minus x square plus y square, right? And x square plus y square is equal to r square. So therefore in this time z varies from 1 minus r square to 4. So this is the corresponding domain in the cylindrical coordinate system, where my domain G is given in the Cartesian coordinate system, bounded by this, this and this. So that means first you have to see what will be the corresponding changes in the domain in the new coordinate system. So that is the corresponding domain in the cylindrical coordinate system. So therefore the corresponding triple integral of my functions f x y z of dx dy dz, that means in the Cartesian coordinate system over G, then this is nothing but this is same as triple integration over d f of r theta comma z, right. Now, if I put it x y z replaced by r theta z, then what will happen? This is nothing but square root of x square, that means r cosine square theta plus r sine square theta, that means it will actually give you 1 r, that is it. So, in other words, you can have it f of what is called x is means what? F of x y z is there, so that means r cosine theta, r sine theta comma z. This is my functions, right. What is my f of x y z? Here I think I should write where f of x y z, which is nothing but square root of x square plus y square. So, that means the corresponding r theta z variable integrand will change, domain will change according to the cylindrical coordinate system which I have written here, and then what will happen? Dr d theta dz, that will be there. Now, extra r will come, so this is a r, and that extra r is coming from the what is called Jacobian business, right. So, that exactly I have written. Now, if I put f of r cosine theta, r sine theta z, what will happen? This is exactly equal to give you r. So, that means r means 2r will be there. So, that is exactly I have written 2r, right. So, but now look at the domain. So, now r varies from closed interval 0 1, theta varies from 0 to 2 pi, but z varies from, it is depending on the r. So, that means z varies from 1 minus r square to 4. So, that means it is clear, that means you have to first integrate with respect to the z variable keeping r and theta constant. So, that exactly I am doing. So, you have to just perform the integral with respect to z variable, where lower limit will be 1 minus r square, upper limit will be 4, and you have to integrate with respect to the dz variable. Now, what is the integrand? Integrand is r. That means that functions r, the z variable is not there in that functions r. That means the function r is independent of z. That means if I perform the integration with respect to z variable first, keeping r and theta is constant, so that you can take out r outside. So, that exactly I am doing. So, first you perform the integration with respect to z variable, keeping r and theta as a constant, and lower limit should be 1 minus r square to 4 because of this domain things. Okay. So, you perform this one z integral first, then you will have something which is a function of r, and then of course, r and theta separate and do the integrations, and if you do that, so this is the value you will get. Okay. So, I think this is clear. So, therefore, if I give some problem that means I say that okay, evaluate that triple integral which is given in the what is called Cartesian coordinate system, or suppose I give some problem, okay, calculate this one, and if you find it difficulties to calculate this integral in the Cartesian coordinate system, sometimes looking at the integrand you may think about to change the coordinate system. That means instead of Cartesian coordinate system, if I change it to the cylindrical coordinate system or spherical coordinate system, whether that can be easy or not to calculate. And answer is, you see, this time it will be very easy, and this is the corresponding integral change of variable formula, and if you perform the integration you will have 12 pi by 5, which is nothing but the triple integral you wanted to calculate. So, this is an applications of what is called change of variable formula. Okay. So, this is for the what is called cylindrical coordinate system. Now, what will happen in the what is called spherical coordinate, similar kind of things. Of course, this time x, y, z has a relation with r, theta, z, then you will see spherical coordinate system, there is a new coordinate system, and also I need to have the relations of x, y, z in terms of that variable, and perform the Jacobian and exactly do the same process. You will have the corresponding change of variable. Using the change of variable formula, you can convert your triple integral from the Cartesian coordinate system to the spherical coordinate system. Okay. So, that is what I have written. So, spherical coordinates. So, R3 spherical coordinates, what is that? So, spherical coordinates are useful when there is a center of symmetry that we can take as the origin. So, that means origin is the center of symmetry, then the spherical coordinates which I denote as the variable rho, phi and theta of a given point A, and it is shown in the following figure. Okay. So, what is that? This is a sphere. Okay. There is a typo, I think this point P, this should be actually A. Okay. There is a typo. So, what is that? So, this is first component is rho, second is phi, and third is theta. What is rho? So, the point if you take in R3, so what is rho? Rho is nothing but the distance from the origin of the point P. Suppose P is x, y, z. So, rho is nothing but square root of x square plus y square plus z square. Okay. So, this is the distance from the point from the origin, that is rho. What is phi? Phi is nothing but this angle. Actually, I am measuring the angle from the positive z axis to the line joining origin to the point P. So, this is the phi, and so phi varies from, actually I will take phi varies from 0 to what is called pi. And what will be theta? Now what I will do, so once I have the point P, then I will take the projections of my point in the xy plane. If I take the projection, it will hit it here. Okay, so this is the corresponding point, this is the projection. Okay, and what is my theta? Theta is nothing but the angle. So if I have a projections of P in the xy plane, suppose this is my point, then you just draw a line from the origin to that point, and what will be theta? Theta is nothing but the angle in the anti-clockwise direction from the positive x-axis, that is theta, and I will vary theta from 0 to 2 pi. Okay, so rho is the distance from the origin, phi is the angle from the positive z-axis to the line joining from the origin and P, and that varies from what is called 0 to pi, and theta is nothing but take a projections P in the xy plane, get a point, then again draw a line from the origin, and theta is measuring the angle in the anti-clockwise directions from the positive x-axis. If I have this coordinate system, I am just writing as rho, phi and theta, that will give you the what is called spherical coordinate system. Okay. Actually, I have written so spherical coordinates. So rho, as I said, if I have a point x, y, z, which is nothing but the distance from the origin, which is nothing but square root of x square plus y square plus z square. Now look, the radial coordinate rho is the distance from the origin O to A, as I said. So rho is always non-negative and is 0 only when A is coincide with the origin. So rho is 0 if and only the point A coincide with the origin. So otherwise rho is always positive because it is the distance from the origin to the point x, y, z. Second one that I am denoting as phi, this is sometimes called the latitude angle. So what is this second spherical coordinate? So first one is the rho, second one is the phi. The second spherical coordinate that I am saying as latitude angle, this is phi, which is the angle measures down from the z axis to the line OA, that is the angle from the positive z axis to the line OA, so that it is restricted to the interval 0 to pi. So look at the things exactly. This is the positive direction of z axis, and this is my point A, this is the line. You just take the angle from positive x axis to the line joining 0 to A. Okay, I have written P here, so P is by typos, it is the point A. Okay, so this is as it is phi, but I actually want that phi should vary from 0 to pi. This is called latitude angle. So this is latitude angle, this angle is called latitude. Okay, and the one theta, what is it that I am saying as a longitude angle? That means the third spherical coordinate, first one is rho, second one is phi, third one is theta. Theta, which is same as the polar or cylindrical coordinate system like r and theta, okay, cylindrical coordinates, and it is the angle between the positive x-axis and the, as I said, projection of OQ of OA. That means you have the line OA, right? Then you take the projection. So what is this? So that means this is the line OA. So this is the line OA, and you just take the projection, and that I am denoting as OQ. So this is the projection in the xy plane. That's exactly I have written. So this is the projections OQ of OA in the xy plane. Usually we will restrict theta from the interval 0 to 2 pi. Okay. So rho is perfectly all right. It is nothing but the distance from the origin. Phi is the latitude angle. I am varying from the positive x-axis to the line joining origin and the point A. Okay, and that should vary from 0 to pi. I want that should vary from 0 to pi. And what is your angle theta? That means you have the line OA, take the projection in the xy plane, and theta is nothing but the angle from the positive x-axis in the anti-clockwise direction, and I want that it should vary from 0 to 2 pi. So there is a small note I have written. It says that incidentally, some books give spherical coordinates in order. Instead of rho phi theta, it gives actually rho theta phi, where theta and phi are reversed. So latitude angle and longitude angle, they somehow change it. So phi theta becomes theta phi. Okay, and you should watch out this when you read it elsewhere. Yes, that's okay. So that means many books, so they have written like instead of rho phi theta, rho theta phi, but you see that which angle, whether it is theta or phi, it varies from 0 to pi or 0 to 2 pi. So depending on that, you will say that whether it is a latitude angle and longitude angle. Okay, that you have to be careful. Different book has a different kind of notations. Okay, so I just tried to give a pictorial things. So like for example, this is my point. So rho varies from 0 to which is called rho naught, and theta and phi is fixed. So fixed theta, fixed phi, you will have a point, and that point rho is nothing but rho naught, that is the distance. Okay. Now what I want here phi varies, that means the what is called latitude angle. So latitude angle, it varies from 0 to phi, where the longitude angle theta is fixed. So that means it varies from in this way. So that's exactly. okay, because I am just varying the latitude angle phi, right. Longitude theta is fixed, right. Longitude theta is fixed, latitude angle, the phi, the point varies in this way. And what will happen in the theta varies? So, theta varies, that means it varies in this way actually, right, because you have the point, so it varies from this ways, from 0 to 2 pi. So, that is kind of figure I tried. So, it depends, you will see that once I have this what is called r phi theta business, where r rho, or I think say rho of phi theta is there, where rho is the distance from the origin from the point x, y, z, and that phi is what is called latitude angle, varies from 0 to pi, and theta is the longitude angle, which is nothing but the what is called polar coordinate system or cylindrical coordinate system. It varies from 0 to 2 pi. So, if you fix phi and theta, then you will have the rho, then you will have the corresponding point in the what is called R3. So, that means if I have a point x, y, z in R3, then that same point I can represent in terms of rho, phi and theta. Like in the cylindrical coordinate system, I can write same point, I can have the representation in terms of r, theta and z. Now, this time I am changing to r, rho, phi and theta. Okay. So, again I just try it. So, suppose this is the kind of spherical coordinate system. So, this is your origin. Suppose this is my point P, earlier actually this is actually A. So, this is the what is called radial distance. So, this is the radial distance. What is called latitude angle is nothing but this one. And what about the longitude angle? So, I have written. So, longitude angle is this one. Okay, that is the point. So, same point. So, this is the corresponding what is called longitude angle, this is the latitude angle, and this is the what is called the radial distance. Okay. So, that is I have written. So, spherical coordinates, longitude, latitude and the radial distance. Okay. So, as I said, so since I am in the spherical coordinate system, then there should be a relations between the Cartesian coordinate system, that means x, y, z in terms of rho, phi and theta. And what is that? So, look. So, okay, what I have written? Oh, okay. So, this is the relations between spherical coordinate system and cylindrical coordinate. Sorry, it is not the Cartesian coordinate system, it is actually the cylindrical coordinate system. Of course, there is a relations of course in terms of x, y, z, but here I put a remark that there is also a relations of cylindrical coordinate system and spherical coordinate system. What is that? So, this is the cylindrical coordinate system, right, r, theta and z, and this is the corresponding what is called spherical coordinate system. So, here r is equal to rho sin phi, z is equal to rho cos phi and theta is equal to theta. So, that is the kind of relations between what is called spherical coordinate system and cylindrical coordinate system. Okay. So, that means of course, I will see that if I change the Cartesian coordinate system corresponding to the what is called spherical coordinate system, how the change of variable formula will help you to get your triple integral in the new coordinate system, right. But this is also true, that means if I have something given in the say spherical coordinate system or cylindrical coordinate system, then you can also kind of change the coordinate system. That means something is given in the spherical, you can change it to what is called cylindrical, something is given in the cylindrical, then you can change it to spherical, and this is the relation. This is, that's what I am put it as a remark. Okay. So, the relations between spherical coordinates and cylindrical coordinate system. Okay. So, that means r is equal to rho sin phi, z is equal to rho cos phi and theta is equal to theta. So, this is actually cylindrical coordinate system and this is actually what is called, this is cylindrical, this is cylindrical and this is spherical. Okay. Okay. So, now in the spherical coordinate system, as I said, so that means if I given the triple integral in the Cartesian coordinate system, then what will be the corresponding triple integral in the new coordinate system, that is spherical coordinate system, using the change of variable formula. Okay. So, now let D be a simple region in R3. Suppose this is the triple integral is given, that means integration of f over the domain D with dx, dy, dz, that means dB. Then the corresponding integral in the spherical coordinate system, it is nothing but you will have a new function which depends on rho, phi and theta. Domain will change depending on the transformation, that means what will be the change domain in your what is called spherical coordinate system, and you see you have d rho, d phi, d theta, that will be there like dx, dy, dz, but now the extra factor is coming and that is coming actually from what is called the Jacobian business. In the cylindrical coordinate system, from Cartesian to cylindrical, you will have the r factor, only r, but this time in the spherical coordinate system you will have rho square sin pi. Again in my next class I will talk about that. If we have the once I will write the transformation, what is the corresponding transformation from what is called Cartesian coordinate system for in the spherical coordinate system, using the transformation, if you just calculate the Jacobian and take the absolute, you will have this one. Okay. So, I have written where D star is the region corresponding to D in the Cartesian coordinate system. I am just writing it as a rho phi theta space. So, I have a D in the xyz space, that is in the Cartesian system. Now, I am changing to a rho phi theta space, that is in the spherical coordinate system. D changes to D star. F of xyz changes, I am just writing, if I replace x by in terms of rho phi and theta, y if I write in terms of rho phi and theta, and z if I write in terms of rho phi and theta, the corresponding integral will change. And that means I will get a function which depends on rho phi and theta, that I am writing as capital F, and then you have d rho, d phi, d theta will be there. But you will have an extra factor which is rho square times sin phi, and that is actually coming from what is called the Jacobian business. Okay, let's see if I calculate the Jacobian, it will be there. So, I have calculated. Okay, so this is the transformation. Okay, so T of rho phi of theta, which is nothing but rho sin phi cosine theta, rho sin phi sin theta, and rho cos phi. So, that means if I have, so that means you can write it as what? So, this is, you can write x of what is called rho phi theta, this is y of rho phi theta, and this is what? Z of rho phi and theta. So, therefore, what is your x? X rho phi theta, which is nothing but rho sin phi cosine theta, y of rho phi and theta, which is rho sin phi sin theta, and z of rho phi and theta, which is rho cos phi. So, any point x, y, z in the R3 in the coordinate system R3 or the Cartesian coordinate system, the same point I can represent in terms of spherical coordinate system, where x can be represented as rho sin phi cosine theta, y can be represented as rho sin phi sin theta, and z can be represented as rho cos phi. So, that is why x is a function of rho phi theta, which is nothing but rho sin phi cosine theta, y is again a function of rho phi theta, which is nothing but rho sin phi sin theta, and z is also a function rho phi theta, which is nothing but rho cosine of phi. So, now I have a x, y, z, same point I can write in terms of what is called rho phi and theta, and this is the corresponding formula. So, then what you have to do? You have to just calculate this Jacobian, that means del x del rho, del y del rho, del z del rho, and then del y del rho del. Okay. So, I think I should write it. So, what is this? This is, if I write it, so this is the 3 cross 3 matrix we will get. So, this is at least del x del rho, del x del phi, and del x del theta. Then you have del y del rho, what is called del y del phi, and del y del theta, and finally you have del z del rho, del z del phi, del z del theta. So, this is the 3 cross 3 matrix. This is a Jacobian matrix of your linear transformation, okay, at the point rho phi and theta. Okay, that Jacobian matrix you have to take the determinant, get the Jacobian, and take the absolute. Okay. If I do that, so what will happen? Look, so del x del rho, so x is a function of rho sin phi cosine theta. So, if I take that partial derivative of x with respect to rho, what will happen? This rho, if I take the derivative with respect to rho, so that means this is guess 1, and this is constant, right? Sin phi cosine sin of phi cosine theta. So, as it is, not a problem. Then del x del phi, that means keep rho and theta constant. So, you have to take the derivative of sin theta, sin phi, that means cosine phi, that means rho cos phi cos theta. If I take the partial derivative of x with respect to theta variable, that means keep rho and phi constant, that means rho sin phi will be there, and take the derivative of cosine theta, that means minus sin theta, that means this is nothing but minus rho sin phi sin theta. Similarly, perform the derivative of y with respect to rho variable, y is given. So, that means if I take the partial derivative with respect to rho variable, that means this is give you 1, that means sin phi sin theta, that's as it is. Okay, del y del phi, okay, keep rho and theta constant, take the derivative of sin, that means rho of cosine phi sin theta, and finally you have to take the derivative del y del theta. So, that means keep what is called rho and phi constant, and take the derivative of sin theta, that means it will be cosine theta, rho sin phi cosine theta. And finally, you have to do the same process in the function z. So, that means if I take the del z del rho, so this will give you cosine of phi as it is, del z del phi, that means keep rho constant, that means it is minus rho sin phi, and finally del z del theta, but z has no component or in variable theta. So, therefore, this will give you 0. So, that is the corresponding matrix, Jacobian matrix of your linear transformation at the point rho phi theta. Okay. So, and then you have to perform what is called derivative. If I take the derivative, it will be rho square sin phi. Okay. Correct. So now, but phi is vary from what? 0 to pi, right? So therefore it is always having positive values. So therefore whether I am taking modulus or non-modulus, that doesn't matter. So therefore this is the corresponding extra factor I am getting from the change of variable formula, like from the Jacobian. So therefore the corresponding dv, which I am writing dx, dy, dz, which is exactly equal to, this is the term coming from the Jacobian, and you have d rho, d phi, d theta. So therefore the corresponding triple integral of my functions f over the domain d times dv, which changes to the corresponding domain in that spherical coordinate system. Again the corresponding integral will change. You just replace x, y, z by the corresponding rho sin phi cos theta, rho sin phi sin theta, and rho cos phi. Then this is the extra factor times d rho, d phi, d theta. Clear? So this is the corresponding change of variable formula. Using change of variable formula, you can transfer your triple integral given in the Cartesian coordinate system to the corresponding spherical coordinate system. Okay. So one example, if I do it, then it will be more clear. Yes. So evaluate this integral e to the power x square plus y square plus z square to the power 3 by 2 over the domain d, and d I have given, which is nothing but all those x, y, z, where x square plus y square plus z square is less or equal to 1. That means the solid sphere I am giving. So that means if I just integrate this function f of x, y, z over the domain d, then of course since I am given sphere, so that means you just take the what is called ranges of rho, phi, and theta. Now rho varies from 0 to 1, phi varies from 0 to pi, and theta varies from 0 to 2 pi. So therefore this is the corresponding theta variable, lower limit, upper limit. This is the phi variable, and this is the rho variable. And what will be there? So e to the power x square plus y square plus z square. If I calculate it, where x is equal to, what is x? X is equal to rho sin phi cosine theta, y is equal to rho sin phi sin theta, and z is equal to rho cos phi. If I do that, this will give you actually e to the power rho. So this actually give you the distance. This is, of course, this is, you don't have to do that. X square plus y square plus z square is nothing but the distance of your point x, y, z from the origin. So therefore x square plus y square plus z square is nothing but what is called rho square. So therefore rho square to the power 3 by 2, which is nothing but rho cube, and this is nothing but e to the power rho cube. This is coming from the Jacobian, that means rho square sin phi, and you have d rho, d phi, d theta. Now this is very nice. Okay. So you have the separation of variable, right? This is function of rho, this is function of phi, and you have d rho, d phi, d theta. If you perform the integration, it will give you 4/3 pi times e minus 1. Okay. So I think that's the way you can calculate your triple integral. Using change of variable formula, you can transform your integral from one coordinate system to another coordinate system. But you have to be careful, because if you change one coordinate system to another coordinate system, not only integrand will change, but also the corresponding coordinate system, there might be an extra factor which is coming from the Jacobian, right? On top of that, the corresponding domain also changes. So you have to be very careful. So if I suppose something given in one coordinate system, and if I want to use change of variable formula to make it to another system, that means you have to first see how the domain changes, what will be the corresponding domain in the new coordinate system. Then in the integrand, it will be easy to have the what is the corresponding integrand, because the corresponding xyz is replaced by the corresponding function as a new coordinate system. That part is okay. But there could be an extra factor, that's actually the Jacobian, and that Jacobian you have to calculate, and that will give you something times the corresponding new coordinate system. Okay. So once I have this transformation, then there kind of you can solve many problems, like many triple integral, which you might find difficulties to solve or to calculate in one coordinate system, but you change it to another coordinate system and solve it. I think that will be easy. And that's how the kind of usefulness of your what is called change of variable formula. You are having difficulties to calculate that triple integral in that system, so let's make a change of variable to in a new coordinate system, whether it might be easy to calculate in that system, and it will give you the same value that you wanted to calculate. Okay. So I think that's all about the triple integral. So I just have the definition of triple integral in terms of Riemann sum, then some couple of example, some easy region I talked about, very simple region. There is a Frobenius theorem how to calculate the full triple integral in terms of iterated integral. Then you have the change of variable formula, then corresponding the changes in the spherical and cylindrical coordinate system, and couple of examples and applications I talked about. I think that's all about the triple integrals. In my next lecture, I will start with something new. Okay. I think I should stop here. Thank you.